Hello everyone. So starting from where we left, which is understanding the basics of probability, we will understand the basics of uh, something called as distributions, right? Now, before we understand the concept of distributions, let's understand something called as random variable. Okay. So what is a random variable? It is a variable that contains the output of a chance experiment. Okay. We discussed what an experiment is in our probability class, right? Let's say, for example, how many goals, how many goals would Messi score in each game? Okay, now that count would be 1, 0, 1, 2, 3, 4, 5, and so on. Let's take a limit. So it could take these values, right? Now let's take another example. How much time does Dhoni take to run between the wickets? It could be 30 seconds, it could be 30.22 seconds, 20.1 seconds, and so on, right? This clearly gives us a classification whether we have one kind of variables or we have different kinds of variables. So we have two. One is discrete in nature, other is continuous in nature. Okay. So today we'll dive deep into discrete distributions, right? Uh, Now there is also one difference that we usually see, that how do people differentiate between these two. Discrete is something which you can count 1, 2, 3, 4, 5, 6, right? And uh, continuous is something which you can measure. Measurement as a word is used for usually things which are not integral in nature. Okay, it can be both integral and uh, continuous variables, but usually it is used for cases where we do not adhere to the integral uh, measurement criteria, right? Yeah. So let's discuss about discrete distributions. So if we say a discrete distribution, how do we visualize it? Okay. So to visualize it, think that for each of the random variable for a chance experiment, we will have a probability, right? Like the cases that we discussed in our probability video. If Messi is to score 0 goals, what is the probability? If he is to score 1 goal, what is the probability? 2, 3 goals, what are the respective probabilities? Let's say 0.37, 0.31, 0.18, and 0.09. Okay. So how will we visualize it? How does it look? Right? This is an expanse of a random variable where it is, let's say, this is 0, this is 1, 2, and 3. It will be, so this is suppose point 1, point 2. something. No, let's not take this measure so that won't be misleading. Let's say this is 0.37, this will be 0.31, this will be 0.18, this will be 0.09. Okay, basically each of the probabilities being represented, each of the probabilities being represented for each of the random variables. So this is how you can visualize a discrete distribution. Okay, now let me bring another concept into play. We call it, so any distribution, as we discussed in normal curve or anything, we need a mean, right, to describe what is on an average going to happen if we look at that event. Okay, that is what mean means, right? For a distribution, we also call it expected value. Right? For a distribution which is uh, probably in this way, where each of the random variables has a probability assigned to it, what could be the mean or what could be the expected value? Okay, now let me tell you about something which is called as long run averages. What does it mean? Suppose, so how is this probability derived? That if Messi plays certain amount of games, in how many games has he scored? Zero, correct? Which would give a probability of this. Similarly for 1 and 2 and 3. Okay, now if we keep on adding for all the games that he has and then we divide it by the number of games, it would reach to a average which is calculated over a long run of games. Correct. Now there is a easier way to calculate the same thing using this probability distribution. Um, I mean, easier in terms of the effort that you will put in writing on a paper, but the concept is same. Okay, we can do this by doing summation of x into probability of x. Okay, now x is an outcome, 0, 1, 2, and 3. Probability of x is the probability of that outcome. Okay, and this is called expected value of x. This is big X, where x belongs to all the values of x. Okay, so if you multiply 0 into 0.37, 1 into 0.31, 2 into 0.18, and 3 into 0.09, okay, and then add them together, you would get a value which is 1.15. Now, what does this mean? That if Messi is to play a game, he would probably score at least one goal. Okay, now because it is saying 1.15, it means let's say if in a game of he plays 6 games, he would probably score 7 goals. Okay, so expected value is same as mean, right? Now similarly, the variance would be calculated as x minus mu whole square into probability of x in the same conceptual logic, right? And standard deviation would be the summation of this. Okay, now if you got the concept of expected value, and from expected value, how do we calculate the variance and standard deviation? Let's discuss some types of discrete distributions and how do they vary in calculating their expected value and in calculating their standard deviation and variance. Okay, we will majorly discuss two kinds. One is binomial distribution, and the second is Poisson distribution. Right? Let's discuss about binomial distribution. Binomial distribution is a case, so it has some assumptions, or it takes into consideration cases where we have n identical trials, where we have two possible outcomes, and the trials are independent of each other. Okay, and we have two probabilities: probability of success and probability of failure. Right? Now, when I say they are independent, it means uh, experiment which occurs after one experiment doesn't have to depend on the previous one, or the previous one doesn't impact its performance. Like picking out a ball from a bag of 10 balls and picking the other ball after replacing the first ball. Okay, the case is like with replacement. If you have seen my probability video, you would have understood that how does a combination work, or the logic of combination works. Okay, and so what would happen if, because we have only two probabilities, one of success and one of failure, if you would do without replacement, then probability of success would change. Okay, which also brings to another assumption, which means probability of success will always remain same. Okay, for this case, the expected value, I hope you understood what expected value is, n into p. Okay, now what is n and what is p? P is the probability of success, while n is the sample space on which you would do this experiment, pulling out from a larger population of n. Okay? Sigma is equal to root over of n into success into failure, right? The coefficient of variation root over of q by np, which also equal to root over of q by expected value. Okay, I'm not deriving these values, but it's pretty simple. If you uh, want to understand the derivation, you can probably get it quite easily, and it is easy to understand also. Okay, now one more concept. So, what would happen in binomial distribution? What you will do, you will also have a way of visualizing it, right? For n being 1, n being 2, n being 3, n being 4, 5, 6, and so on, you will have their respective probability values, right? This forms a distribution. Okay. Now, having those similar concepts of distribution in your mind, we will go ahead and look at more deeper concepts of how do we solve problems which are related to or which comes in the categories of binomial distribution, right? Now, is there a function which can really form these values for a given value of x? Okay, for a given value of x, the probability value is calculated in this way. This is your sample size, this is your trial number or the random variable into p to the power x into q to the power n minus x. Okay, this would give you probability, or also understand it in a way that this is the function of binomial distribution. You use this function, you get these values, or use this function to derive this distribution. Okay, let's see one example to understand the concept a bit better. A Gallup survey found that 65% of all financial consumers were very satisfied with their primary financial institution. Okay. Suppose that 25 financial consumers are sampled, and if the Gallup survey result still holds true today, what is the probability that exactly 19 are very satisfied with their primary financial institution? Okay, the thing to note here in this question is that we have to find out what is P and what other variables, what is N, what is X, right? Gallup survey found that 65% of the financial consumers were very satisfied with their primary financial institutions. Okay, success. Suppose that 25 financial consumers are sampled, your sample space, right? What is the probability that exactly 19 are very satisfied? Somewhere here you have to find the value of 19 and say what is the probability. Suppose it is 19, what is the probability of this, what is the height of this? Okay, and for to find that out, you can use something like this function. Correct. Pretty simple. Okay. Let's look at another example. According to information resources, which publishes data on market share for various products, Oreos control about 10% of the market from cookies brand. Okay, Oreos control 10% of the market. Suppose 20 purchasers of cookies are selected randomly from the population. 20 are selected randomly from the population. What is the probability that less than 4 purchasers choose Oreos? Okay, less than 4 people choose Oreos. Less than 4. Okay, choosing Oreo, right? Now, what is the probability of success here is 10%. Only 10% of the whole market takes Oreo cookies, right? So, probably 10% of whatever you throw at me, the number would take Oreo biscuits, correct? That makes P is equal to zero point 0.1, right? 20 purchasers of cookies are selected randomly. Selection, a method of sampling. 20, right? Now it is asking for what is the probability that fewer than 4 purchasers choose Oreo. X value which is less than equal to 4. Okay, 4 and less than equal to 4, which is 0, 1, 2, 3, 4. You have to find the probability of them and do a sum. Then only you will be able to find what is the probability that fewer than 4 purchases happen or they choose Oreo, right? And you will go everything to the left side of 4. If if you are already doing the analogy with the normal curve that we were learning, you would be getting why do we do or calculate the probability values to the left side or to the right side of any sigma. Okay, because that is also a probability density function or a probability density curve. Just like this is also a probability density curve, right? Now, how do we do this? For x equal to 0, 1, 2, 3, 4, we'll have probabilities which will calculate Cn0, p to the power 0 into q to the power n, Cn1 into p to the power 1, q to the power n minus 1, and so on. And then whatever values you get, you add it. Okay. So calculate the value and give me an answer. Right. Now let's see one more example. Okay, a manufacturing company produces 10,000 plastic mugs per year, per week. Okay. This company supplies mug to another company, which packages the mugs as part of picnic sets, right? Now it produces a sample. It produces as a whole 10,000 mugs, right? The company supplies to another company so and so, and the company randomly samples 10 mugs. Sample size is 10 mugs. Okay. If two or fewer of the sampled mugs are defective, so defective should be less than equal to 2. Sorry, not less than 2, equal to only less than 2. Correct? Then it would not accept the lot. Now, what is the probability that the lot will be accepted if the mug manufacturing company actually is producing mugs that are 10% defective, 20% defective, 30% defective, and 40% defective? Okay, understand the question. A manufacturing company produces 10,000 plastic mugs per week. The company supplies mugs to another company which packages mugs as part of picnic sets. The second company randomly samples 10 mugs out of those 10,000 plastic mugs, and if from those samples two or fewer of the sampled mugs are defective, the second company accepts the law. So sorry, it will be less than equal to 2. Okay, so what is the probability that the lot will be accepted if the mug manufacturing company is producing mugs that are 10% effective? This is one case, one part of the question. 20% is one part of the question. 30% is another part of the question. 40% is another part of the question. Okay. Now, that being said, so what is varying here? What are these? 10%, 20%, 30%. These are the changing probabilities, right? You have the values of x, you have the value of n. What you have to calculate is, if this happens, if with this probability, what is the expected value of x, okay, in a sample of so many mugs, and what is the expected output of this, expected output of this, and expected output of this for these values of x, and then you have to tell whether they will accept or not. Okay. A bit conceptual, but it is easy if you understand the basic. Okay, if you understand what an expected value means and how do you find that out. If you understand that, then probably you would be able to answer this. This is a part of assignment. Okay, a bit thought provoking, but I think that most of you should be able to get this. Okay. Uh, yeah, you can pause the video after this and look at this question and provide an answer to this as well. This is pretty straightforward question. It won't be very uh, difficult to answer. Okay, but because these things are quite uh, fundamental in nature. I would want you to use or think as much as possible, and then let's discuss that how much did you think, and what were you not able to solve or not able to understand. Okay, so that's it. That is about binomial distribution. Similarly, one more distribution which we have is Poisson's distribution. Okay, just like binomial distribution, this also has some assumptions that the value should be discrete. Usually happens for the cases of rare events, not for regular events. Okay, the occurrences that happen are independent in nature, right? And they occur over a period. Okay, when I said that, uh, there are certain conditions which we'll understand more when we do the problems or look at examples. Okay, let me give you sample examples. Now, the number of calls per minute in a customer care of Swiggy, right? The number of people arriving at the Bangalore toll booth, number of bugs in your code or errors, number of errors in your code that you have developed, right? These are some of the examples of Poisson's distribution. Similarly, like binomial case, there here also we have long run occurrences or the expected value or the mean, which we call as lambda. Okay. Now, what is the function of probability distribution? So here also we'll have a way to visualize this. We'll have a density function. And what is the formula for this to arrive at the probability function? Lambda to the power x. I hope you would understand what x means by now. The random variable into e to the power minus lambda by x factorial. Okay, e is equal to a constant which is 2.7182, right? Let's see a simple example. Suppose bank customers arrive randomly on weekday afternoons at an average of 3.2 customers every 4 minutes, right? The average at which you arrive at which the customers arrive is 3.2, okay, in every 4 minutes. Now, what is the probability of exactly 5 customers arriving in a 4-minute interval on a weekday afternoon. What is the probability of 5 customers arriving? Right? You clearly know that this is the value of x. Now, if it is saying that average is 3.2, what could be something? What could be the meaning of average here? The average means long run occurrences or expected value or mean are same and we call it average. In this case, lambda is equal to 3.2. You have lambda, you have x, you have e. I hope you can calculate p to the power x. If you have attended the previous uh, probability class, you would know that what to do for factorial. Okay, this is a simple example. Now, what is the probability? Extension of that question. What is the probability of having more than 7 customers in a 7-minute interval on in a 4-minute interval on a weekday afternoon? Of more than 7. 0, 1, 2, 3, 4, 5, 6, 7, and then there would be after this. Okay, they want the probability of this area, right? You would calculate the probability of values above 7 and do a summation to tell what could be the total probability. Okay, this is part of the assignment, right? Binomial equal to poisson. Acha, okay, yeah. So, so whatever I'm going to tell now is really not important as such, but it is a. I mean, if you know, it would really challenge your thinking process. Okay. Now, there are cases where binomial distribution tends to become a Poisson's distribution. Now, what are the cases? Okay. So this would also tell you, of course, you can probably pause the video here and think of what could be a case where binomial would become Poisson's distribution. Okay. Thinking of it is a really interesting work, but then let me tell you. Okay. So binomial becomes Poisson in a case where sample size becomes high. Is there a rule of thumb? Yes, where the sample size is greater than 20. Okay, and the probability of success is very, very less. Now, why is that so? Because if the probability of success becomes very less, it becomes a rare event, right? Which also means n into p equal to lambda, and so on. So you can keep equating things. Okay, so when I say that, look at this question, pause the video, and I think probably you should be able to solve this. Use the same concept of how binomial becomes poisson, in which case, and how do we calculate. Okay, so that's it for the basic of discrete distribution. I will also be sharing a video about continuous distribution, right? After we do that, I think we are good to go to proceed with hypothesis testing and our machine learning algorithms. Okay, not that as a work of day-to-day data scientist you would really need all of these these concepts, but the thing is these concepts are imbibed in the machine learning algorithms. So when those come up, then you will again face a tussle to understand these concepts, right? Which is why I'm focusing a lot on the basics, so that when whatever complexity comes, or whatever complexity I think I know, you would find it easier to understand, right? I hope you would work on this and give us assignments.